All right, so we'll get started. I want to remind you guys that next homework is up online. It's due by Tuesday next week. Okay. Um, for classroom disinfection today, I assigned to medicine and grant. All right. Um, so last time we talked about the electromotive force. So this is the potential that a battery can supply. It's called electromotive force. It's given as a special name, although the name contains force, but we should take note that this refers to the power or the voltage, okay, the potential here. All right, so symbol is epsilon. You can also use V if you want, okay. So if you move the amount of delta Q from the positive terminal to negative terminal, then work done is equal to the magnitude is equal to delta Q over times epsilon, okay, or Q times V. We also talk about combination of resistors in series and in parallel. So if the resistors are in series, then the current going through each resistor will be the same, meaning they are sharing the same current. If they are connected in parallel, so then the voltage across each resistor will be the same across, okay, for either all of them. So if you have resistors in series, you can replace the combination with a equivalent resistor. The equivalent resistance for this resistor will be equal to the summation of the resistance of each resistor you have in series, okay. If you have the resistors in parallel to each other, then inverse of the equivalent resistance is equal to summation of inverse of the resistance for each resistor. Okay. And we also talk about for complicated scenarios when you have in a circuit both you have the resistor in series and then in parallel together. So you will take step by step. So to just check at the part that you have resistors either in purely in series or in parallel, and then replace that part with an equivalent resistor. So simplify the circuit by doing that step by step. So just basically repeating the process until you get to the final steps that you can represent the circuit with a simple equivalent resistor. Okay. So today we are going to look at some more complicated scenarios. Okay, so up to this point, the circuit we have been looking, they all only have like one power supply in it. Okay, so in sometimes you have more than one power supply in the circuit. So for example, if you have a circuit like this, there are two power supplies, two batteries over here. Then in that sense, so the current, okay, and not simply just from the positive terminal to the negative terminal if that's what's happening for a single source of power. So in this case, you can see power goes from here and then coming in this case. But at this point, you may expect that the current goes here, goes into A, split into two, right? So if that's the case, then it's possible that the current is going through here. So it's actually going into the positive terminal. Okay, so things are getting a little bit complicated over here. When you have complex circuits like this, you cannot simply break this break down that the parts of resistor will be purely in series or in parallel. Okay, so in that case, you'll have to apply certain rules called Kirchhoff's rules. Okay, so there are two rules here. One is called junction rule, and then the other one is called the loop rule. Okay, so for the junction rule, this is basically the consequence of charge conservation. So basically, current is charge. Okay, so when you have current going into a junction like this, it will actually split into two. All right, so it goes one in here in this branch, one in that branch. Okay, so the current goes into a junction will equal to current goes out of the junction. Okay, so that's basically the junction rule. And loop rule is a consequence of energy conservation. Okay, so basically we will say if you are starting from one point going through a complete loop like this, so going from here, comes back over here, then the potential should returns to its initial value. Okay, so that means delta V, if you go to a complete loop, it will be equal to 0. Okay, you can also go through this loop over here. Okay, or you can go like from here and then going through the outer loop here. So there are 3 loops in this circuit, the 2 small ones in the middle, the bigger ones on the outer route there. Okay, all right. So mathematically for junctions rule, this is what you will be writing. So the I goes into a junction will split into 2. Sometimes you might have like more than one current going into one junction. Okay, so then for that you'll just add the 2 goes in, that will be equal to like 2 or more goes out. Okay, so the current goes in equals to the current goes out. Okay, the sum of currents go in equal to the sum of currents go out. Okay, so that in that case, this one is basically I1 equal to I2 plus I3. Okay, so it's the same that as that one. For the loop rule here, all right. So if you go from, say, from point A to B to C to D back to A, okay, then this is what's happening. So you'll be counting on the potential change across each element over here you encounter, okay? So there are certain rules here as well. So if you are going through a battery, if you go from negative terminal to a positive terminal, you see the potential will increase, right? Because the positive terminal will have higher potential than the lower on the negative terminal. So when you are going from a negative terminal to a positive terminal of battery, your potential increase. Okay, so this is increased by epsilon. So then you can write that for this element, when you go through this element, potential increased by epsilon. Okay, and now the next element in this example here is this guy, the resistor. Okay, so if you go from C to D here, all right, that's its change in voltage delta V CD. Okay, so delta V CD then goes back here. So all these changes should add up to be 0. Okay, because the change of potential, if you are starting from point A, going back to point A should be equal to 0. Right now, if you are encountering a resistor, if your loop is going in the same direction, okay, so there's a direction of loop, you go from here to here, there's a direction of current. Okay, now take this note here. So if your loop is going in the same direction as the current through a resistor, then the voltage decrease. Okay, so decrease by, so in this case is I times R. So then the change delta VCD here should be minus I times R. Okay, so then this equation will become epsilon minus I times R equals to 0. Okay, so that's the loop rule here. All right. Just keep in mind that potential decreases when current passes through a resistor. Okay, so if that's the same direction as the loop. Okay, your loop. All right. Now to use Kirchhoff's rules. Okay, so you will be likely looking for a few variables. Okay, not just one. So then you'll need as many equations to solve for the variables. So for example, if you're looking for 3 variables, you will need 3 equations. Okay, you need to set up 3 equations for that case. And then they have to be independent equations. Okay. In many cases, you'll use both loop and junction rules. Okay. So we'll take a look on one simple example here. So in this case, you only have one loop here. Okay, so there's no junction in the circuit, right? So it's asking you to find the magnitude and direction of the current in the figure. Okay, So I think let's see. So we'll see about this one here. Okay. Let me redraw the circuit over here. So 15 volts here, 11 point volts there, 8.5 ohms, 6.22 ohms, 15.1 ohms. Okay, so this is a very basic example of just the loop rule here, because you only have a loop here, you don't have junction. That means you don't have like a current goes in and then splits into 2 or 3, or maybe like 2 comes in, merge into 1. Okay, in that scenario. So in this case, you can see so you can pick the direction of your current. Okay, you can assume. So this is the trick here. So many times you are not actually 100% sure what will be the direction of your current, right? So, but you can make an assumption that the current, if the current in this case is going in this direction, okay. So let's say this is the direction the current is flowing, okay, the clockwise direction. All right, then you can set up the equations, and then at the end, when you solve for this I, okay, if I is negative, so that just says your initial assumption for the directional current is not right. Okay, so it should be in fact in the opposite direction. Okay, um, so in this case, because this is 15, this guy is 11.5. So I think this is higher potential difference than this guy. So I would assume that the current is going in this direction. Okay. All right. So we'll apply loop rule only because we don't have a junction here. So let's start from this point, starting point. All right. So we are going in this direction for our loop. Okay. So this is our loop direction. All right. So you are going across a battery here from negative terminal to positive terminal. So then the change in potential here is positive. Okay. From negative terminal to positive terminal of battery increase. Okay. Now you are going through a resistor. All right. So, and that's the direction of current. That's your loop. So then potential across a resistor here will be negative. Okay. So negative of I times the R according to Ohm's law, okay? I times 8.5, okay? And this guy over here, again, you are going from negative terminal to positive terminal of battery. So then your potential will increase again, okay, plus of the amount. And then on this resistor, you are going in this direction, the loop also goes in that direction. So it'll be minus I times 6.22 ohms, okay? There's a third resistor here. The current direction and the loop direction are in the same direction. So then it's again minus I times 15.1 ohms. Okay, that will equal to 0. Okay, junction rule should be simple to write, but loop rule sometimes might be confusing. Okay, so again, if you go from negative terminal about a battery to the positive terminal, then potential increase. If you are going from positive terminal of battery to the negative terminal in battery, then potential decrease. Okay, and if your loop goes in the same direction as the current going through a resistor, then potential drops. Okay, or decreases. if you pick your loop to go in this direction, so then it's against the direction of the current. So then when you're going through a resistor, that potential will increase. Okay. All right, but in here, we can take a look over here. So you are looking for I. All right, so these three terms have I in them. You can put them together and then move them to one side of the equation. You can solve for your I. Okay, so on the left hand side, you can have 15 plus 11.5, and then you can move those three to the other side of the equation. So 15.5 plus 11.5 will be equal to I times 8.5. Okay, and then you can put this together, 6.22 plus 15.1. Okay, they are all in ohms. Okay, so that means you move them to the other side equation. Then you can solve for your I. So divide both sides by this, 8.5 plus 6.22 plus 15.1. Okay, to solve for your I. Okay, so in that case, I will be equal to 0.889 amps. Okay, so it shows that this I is positive. So that means your original assumption for the direction of the current is correct. Okay, so your I, that's the magnitude, and then direction will be clockwise direction. Okay. Questions you guys might have? All right. If not, we can take a look on this a second example here. Okay, so although this one has only one battery in it. Okay, so basically we can use the knowledge we learned last time. So we did that last time, right? We were looking at this circuit last time, and then we figure out what the current through each of the resistors last time, right? So we basically treat like the circuit like looking at the part that is purely in parallel or in series, and then doing the equivalent resistance to replace that part, and then multiple steps we simplify the circuit. But as we have talked about Kirchhoff's rule, so we can indeed actually apply Kirchhoff's rules this time here. Okay, so let me just show you how you can actually apply Kirchhoff's rule here on this one, and then we can compare our results to what we got last time. Okay. So in this case, you have there's this junction here. Okay, splits into two. So you can see this is 15 volts. We can assume again this battery, the current goes out of the positive terminal, all right, that goes into this junction point B. And this is, so let's call this I1, all right, and then it becomes I2, and then I3. Okay, we can assume in that way. Okay, so then there's one junction here. You can apply your junction rule. This is 6.2 ohms. This is 12 ohms. This is 7.5 ohms. This is 11 ohms. Okay. All right. So for junction rule, you It basically says currents go into one junction should be equal to current go out from the go out of that junction. So I1, you can write I1 is equal to I2 plus I3. Okay, simply like that. Now there's another junction here at this point where I3 comes in, I2 comes in, and then goes out the I1 there. Okay, so this is the same equation if you apply junction rule here, and the same as that one. Okay, so then those two are repeating each other, so you can just use one of them. Okay, so you don't you should, yeah, you don't want to write the other one down because it's identical to that one. All right, now for loop rule, so I1, I2, I3, they are unknowns. Okay, so that means you have 3 unknowns here to solve for. All right, you'll need 3 equations. We have 1 equation now. Now you need 2 more equations. Okay, so you can apply loop rule twice. Okay, so in this case, you can pick a loop here. You can take this loop. All right, you can say this is your loop 1, and then that's the direction you want the loop to go. And then you can pick this as your loop 2. Okay, this is your loop 2. All right, so if you apply loop rule on loop 1, you'll get 1 equation. If you apply loop rule on the second loop, you'll get a second equation. Okay, so let's do that. I'm going to start from this point at the bottom here. So the first element I encounter is this battery. Okay, I'm going from negative terminal to positive terminal again. That shows that my potential should increase by the amount of 15 volts. Okay. Now in this loop, the second element you encounter will be this resistor. All right. So this is the direction of loop. This is the current goes in this, go in the same direction. So that means your potential will decrease, okay, by the amount of I. Okay, now this is the I. The I3 is the I going through this guy. Okay, you'll take that as your I. So that will be 7.5 times I3. Okay, I times R or R times I. Okay. I'm going to leave out the unit here because they are all in SI units. So let's just take the numbers. So 15 minus 7.5 I3. Okay. In this loop, the second resistor you encounter will be this guy. All right. And then the current goes through in that direction. Okay. So that means minus 11 ohms times I1. Okay. So pay attention to what I you should use. Okay. So it should be the current going through that resistor. Okay. Then you go back to your original starting point. So that will give you 0. Okay. The potential change when you complete a loop should be equal to 0. All right. Now on your second loop, you apply that again. The loop rule again. Okay. So let me see. Okay, I think on my note I put this as I3, I2, this is I3, but that's fine. We will stick with what we have on the paper here. So it doesn't matter. Okay, so on this one, so you can start from anywhere you want, but I'm going to start from here, this point. Okay, I'm starting from this point. So I encounter this guy, this resistor, and this resistor. Okay, in the same direction of the loop. Okay, so that would be minus. Okay, minus of I2 or minus of 6.2 I2 times 6.2, and then minus I2 times 12 ohms. Okay. So now on this guy here, on this resistor here in this loop, okay, you are going in this direction. Your loop goes in the direction against the current, okay? So then voltage will increase, okay? So if your loop goes against the direction of the current, your voltage will increase. So plus 7.5 I3 goes to 0, okay? So now you have 3 equations down here. So 1 equation, 2 equation, and 3 equations. Okay. And then you can solve for your 3 unknowns, okay? You'll be using substitution, all right? We'll do it this way. So we'll write, so this I1, I3, that's I2, I3, okay? So that's, you can combine these two, right? So this will be 12 plus 6.2 will be 18.2 times I2 minus, right? Plus 7.5 I3 equal to 0. So you can basically rewrite this guy. Put I1 in terms of I3, right? So that means you can write 15 minus 7.5 I3 equals to 11 I1. So then I1 will be equal to, let's divide by 11, okay? Divide by 11 there. I1 is equal to 15 minus 7.5 I3 divided by 11, okay? On this one here, you can write I2 in terms of I3, okay? So you can move this guy to the other side of the equation. So then becomes 7.5 I3 equals to 18.2 I2, okay? Divide both sides by 18.2 will give you I2 in terms of I3, okay? Then you can do substitution. You can put this substitution as I1 here, and then this substitution as your I2 over here, okay? So you can write 15 minus 7.5 I3 over 11. This is your I1 equals to I2 is this guy, 7.5 I3 over 18.2 plus I3. Okay. So you can see now in this equation, you only have I3 as your unknown. Okay. So you can solve for your I3. All right. So basically, there should be two terms on this guy with 15 over 11 minus 7.5. Okay. So this will be 15 over 11 minus 7.5 over 11 I3 equals to 7.5 I3 over 18.2 plus I3. Okay, you can isolate I3. So put this to the other side of the equation and then solve for your I3. All right. So yeah, I think you can do this, just a couple steps of algebra here, but I'm going to just write down the final answer I got here. So I3 here, it should be 0.651 amps here, okay? If you do this, solve this correctly, that should be the number you get. All right, so once you have I3, you can put I3 here to solve your I1. Okay, you can solve for that. I1 can be solved. That will be equal to 0.92 amps. Okay, and then similarly, put I3 here, you can solve for your I2. Okay, so I2 will be equal to 0.27 amps. Okay. And we can see I3 is the 7.5 ohms, okay, resistor. For I1 is the one going through the 11 ohms. You can specify that. It's for that, for 7.5 for 11 ohms. And then 0.27 is for the 6.2 ohms and the 12 ohms, okay. And if you compare this to your notes on what we got last time, no, not here. All right, this is what we got last time. Last time we got 0.27 for 6.2 and 12 ohms, okay, which is this guy, all right, and then we got for 7.5 ohms, it's 0.65, Okay, it's that guy. All right, and then for 11 ohm is 0.92. It's this guy. 11 ohms 0.92. Okay, so that's the same answers. Okay, so either way, if you have a circuit like this, you can actually also do loops, the Kirchhoff's rules. Okay, and then if you think you are more comfortable of doing this way, then you are welcome to solve the problem in this method. Okay. All right. Questions you guys might have? Okay, so if you are clear with that, so then I will have you guys try to solve for this one. Okay, so you can apply Kirchhoff's rules here. You can write one equation out of junction rule. You can write two more equations out of the two loops. Okay, loops rule there, and then try to solve for the current goes through each of the resistors shown in the figure below. Okay, and we can take a look at the solution in a few minutes together. So if you want, you can use the same notation as I do here. So I want to go into this junction, and then I2 goes in this one, I3 goes in that one. Yeah, and then I take this as loop 1, this as loop 2. I have both loop in the clockwise direction. All right. So let's take a look here. You can apply junction rule once. Okay, so at this junction there, and then on this junction will be the same equation that you obtain from here. Okay, because I2 comes in, I3 comes in, becomes I1 goes out. Right? So those two junctions will give you identical equations. So we'll just apply one of them. So I1 equals to I2 plus I3. Okay, for junction rule here. All right, now you have one equation, you need two more equations. You apply loop rule to loop one and then loop rule to loop two, okay? I will start from this point again. So this is the direction of loop. So I'm going through the negative terminal to the positive terminal. So my potential will increase. Okay, so for loop one, this will be 12 volts, okay? Now I have I1 here in the same direction of the loop, okay? So then negative 3.9 I1, your potential will drop there. And then I take I2 to go down here. And then loop also goes down there. So minus 12 I2, okay? Now for this guy, I will have, again, minus because that's the direction of my current. That's, I'm assuming that should be I1, okay? So that should be I1. And then the loop also goes in that direction. So minus, again, minus 9.8 I1, okay, equals to 0. Okay, I return to my initial starting point. Okay, so that's my loop one. For my loop two here, if I start from this point where the current split into I3 and I2, so then, and I'm assuming this is my loop. Okay, so I3 and loop 2 are in the same direction. So you start with minus 6.7 I3 for the potential decrease across this guy. And then on this guy here, battery, you are going now, this time you are going from positive terminal to negative terminal. So that's minus 9, okay, the voltage. And then for this loop 2, the next element you encounter will be this resistor, 12 ohm resistor. So your loop goes in a direction against the current. Okay, so then your voltage will increase. So plus 12 times I2. Okay, and that goes to 0. Yeah, coming back to your original starting point. Okay, so you have three equations. You have three unknowns. You can solve for the unknowns. Okay, so let's take a look here. So in this equation, you have I1 and I2. All right. In this equation, you have I3 and I2. Okay, so both equation, the common current you have is I2. So you can write the other unknowns in terms of I2. Okay, so in this case, you can write I1 in terms of I2. All right, so that means you'll isolate I1 to one side of the equation. So this is 12 minus 12 I2 equals to I1 goes to the other side, 3.9 plus I1 plus 9.8 I1. Okay, so these two add up to be 13.7. So this is 13.7 I1. So then you divide both sides by 13.7 to get I1. Okay, so I1 equals to 12 minus, wait a second, this, is this resistor 12 or 1.2? It's actually 1.2 here on this guy. This is 1.2, okay, 1.2 ohms, my mistake there. So this is 1.2, 1.2 are I2, 1.2 of I2, okay? So your I1 is equal to 12 minus 1.2 I2 over 13.7, all right? Now you can write on this one, you can write I3 in terms of I2, okay? So you're going to isolate I3. So that means this is 1.2 I2, okay? It's this guy. So this is 1.2 I2 on the left-hand side minus 9 should be equal to, you move this guy to the right side, 6.7 I3, okay? So then I3, you divide both sides by 6.7. I3 is equal to 1.2 I2 minus 9 over 6.7. Okay. Then you'll be doing substitution. So this is your I1. There in the first equation, this is your I3. All right. From there, so I1 you can write now. I1 12 minus 1.2 I2 over 13.7. That's I1 equals to I2 plus I3 1.2 I2 minus 9 divided by 6.7. Okay. So then here you only have I2 in the equation. You can solve for your I2. Okay. So this would be two terms over here. So 12 over 13.7 minus 1.2 over 13.7 times I2, right? Equals to I2 plus 1.2 over 6.7 times I2 minus 9 over 6.7. Okay. To solve for I2, you'll move I2 to this side. You'll move this guy to the other side. Okay. So then you get 12 over 13.7 plus 9 over 6.7 equals to, those three add up together. Okay, so 1.2, 13.7, I2, okay, plus I2 plus 1.2 over 6.7 I2. All right. So then this is 1.2, 13.7 plus 1 plus 1.2 over 6.7 times I2. Okay. Then you'll solve for your I2. So basically this guy over this guy. Okay, so 12. This is 12, not 1.2. 12 over 13.7 plus 9 over 6.7. Okay, on the top, divide by this guy at the bottom. That's equal to your I2. Okay. So it's going to give you your I2 as 1.752 amps. Okay. Once you have that, take your I2 there, you can solve for your I1. Okay. So then I1 is equal to 12 minus 1.2 times 1.752 over 13.7. That would be 0.7225 amps for your I1. Take 1.752 as your I2 here. You can solve for your I3. Okay, so your I3 is equal to the 1.2 times 1.752 minus 9 over 6.7. Now that gives you minus 1.029 amps. Okay. All right. So this guy is minus. I3 is minus. Okay. I1 and I2 are positive. I3 is minus. Okay. So that actually tells you that your initial assumption for the direction of I3 is not correct. Okay. So indeed, your I3 will be in that direction. That will be your I3 direction. Okay. So I1 and I3 goes in becomes I2. All right. That's basically what it says. Okay. Your direction of I1 and I2 are still fine, but I3 is not. It's in the opposite direction. Okay. So when you get negative sign, that's what it means. Okay. So don't be surprised if you get a negative sign on your current. Okay. Just says your original assumption for the direction of the current wasn't correct. All right, questions you guys might have? So if not, we will move on, but you guys will get, I think, two problems in the next assignment, okay, to practice on the Kirchhoff's rules. All right, so next, we'll talk about the multimeters that you guys have been using, okay? So for multimeters, you have different settings, okay? The fact it's called multimeters because it can measure current, voltage, and resistance, okay, for multimeter. So that's the multi-purpose there. But when you are using a multimeter for a current measurement, then you are using the setting of called ammeter. Okay, so that's the ammeter there. So it measures the current. All right. And then if you are measuring voltage, then you are using the voltmeter. Okay, so by switch it to the voltmeter setting, you are measuring the voltage. Okay. Um, so when you are measuring the current must flow through the ammeter. Okay. So then in that sense, you want to have your measurement as accurate as the circuit should be. So by inserting a ammeter, you don't want to disturb the current very much, or you don't want to alter the current very much, right? So then for ammeter, its resistance is very small. Okay, so that means compared to the elements, it's very small. It will not disturb the current very much. Okay, so then that's why when you guys are using ammeters, be very careful because the resistance is very small. If you apply any voltage across it, then it will cause a lot of current going through it. Okay, so then it will burn the fuse inside it. So then it will burn the ammeter. So for some, occasionally, when you guys are given a multimeter, um, it's not measuring the current, so that means it's likely that the fuse is being burned, okay, due to not so careful operation of it. So that's why in the lab, when we are doing the lab, if you have an ammeter in the circuit, make sure you have the switch open while you are doing the changes, okay? So, and then you just want to turn it on after you are sure about it's not in a short circuit, so then it will not be burned, okay? So just pay attention to that when you are using an ammeter, okay? When you are using a voltmeter, so you are measuring the voltage across a resistor, okay? So in that sense, you want to have the voltage as close as it should be. So then for the voltmeter here, actually it has very large resistance, okay? So in that case, then the current is not going through the voltmeter very, or it's for the current going through the voltmeter, it's actually very small compared to the current going through the resistor you are measuring, okay? So in that sense, that when you are doing using a voltmeter, it's you usually don't have to be as careful as you are using an ammeter. Okay, so it should be very safe to use a voltmeter in the sense that you will not burn it. Okay, all right. For ohmmeter, it actually measures the resistance of it. Okay, so in that sense, it's also a lot of times, yeah, you don't have to be super careful about using an ohmmeter. Okay, it basically measures the resistance of an element. So yeah, and then for an old style ohmmeter, it might be you might be seeing that it's the scale is in the logarithm scale. Okay, increment of like 10 times. All right. Um, I think, yeah. We'll talk about this later on Friday on the when you have So a lot of times you are not having just purely resistor in the circuit or capacitor, but you might be having like combination of resistor and capacitor. Okay, so then things a little bit tricky there. We'll talk about it on Friday. Okay, so we'll stop here for today.